This talk is called Cameras and the Geometry of Vision. This is an eyeball. I'm going to start by talking in some detail about how the world looks to an eyeball. But there's an analogy between the eye and the camera that's actually quite explicit. Both of these have a lens and an aperture up at the front. They both have a gap in the middle across which light gets focused. And they both have a light-sensitive surface in the back. In the case of the camera, that's a piece of film or a digital sensor. And in the case of the eye, it's a sheet of nervous tissue called the retina. So the camera actually sees the world the same way we do. And the invention of the camera really helped us understand some peculiar things about how we see. So to understand what's so peculiar, imagine an eye traveling around in a field of objects. And something to notice is that these objects are all about the same size, and they're all fixed in place. And because all of us look through eyes all the time, we should have a reasonable idea of what this must look like to the eye. So hopefully it's not too hard to connect the point of view shot on the right with what's happening on the left. But if you look closely at what the eye is seeing, it's not exactly what's out there. All the stuff that's nearby looks really big, and all the stuff that's far away looks really small. So if you were to take your eye at its word, your kind of naive impression might be that the world was behaving a little more like this. Things sort of swell up as you get close to them, and they shrink down as they get far away. So your eye is actually lying to you all the time about what the world looks like, and it's a lie that we call perspective. And we understand implicitly that the world is as we see it on the left there, which I'm going to call the isometric view. But our experience, our visual experience of the world is what we call the perspective view. And we're so used to seeing things in perspective that we rarely notice how preposterously distorted our visual experience is. And in fact, for most of human history, representational art was pretty much strictly isometric. Everything appeared at a single uniform scale, and there wasn't a bunch of depth. In medieval times in Europe, there was some effort to represent the world not as it is, but as it appears to the eye, and this led to this kind of awkward phase where we were playing with scale a little bit and representing things from different angles, but it was all kind of ad hoc, and it didn't really work. It was clear that there were some rules to perspective, and we didn't really know what they were yet. And that's understandable because perspective isn't out in the world. It's happening basically inside your eye. And it's really hard to measure what's happening inside your eye. So this is a device for making those kinds of measurements. This one's known as Alberti's veil. There's a little peephole that keeps the artist's eye fixed at a certain location. And then he's put up a wooden frame with a grid, and he's sort of transcribing square by square what he sees. And there were a bunch of these. Leonardo da Vinci had one called Leonardo's Window, and he actually drew right on the screen itself. We have an exhibit called perspective drawing window, which is this same idea. Basically, it's a device that lets you make a rendition of a three-dimensional scene with the perspective intact. And not only does this allow you to make perspective images, it allows you to study perspective and try and back-solve what the rules are. So consider this example of bad perspective. There's a lot of hilarious things that are wrong with this picture, but the thing I want to draw your attention to is the floor. It's a checkered tiled floor, but you can see it's all just vertical and horizontal lines, and that's not right. This is what a checkered tiled floor really looks like in perspective. So it's got this kind of oblique quality to it, and it diminishes in a very gradual way, and it actually looks really beautiful. So this was a classic problem from perspective theory. How do you draw a checkered tiled floor in proper perspective? So to understand why this is so hard, let's just look at a single tile from a checkered floor. What makes this tile square is the fact that it has 4 equal sides, and they're connected by 4 right angles. So we're going to zoom in on this tile, and let's bring in an Alberti's veil, and let's just examine how it works in perspective. And to make things a little simpler, we'll also bring in a simultaneous side view so we can see what the tile is doing in space and compare it to how it looks in perspective. So viewed straight on like this, the tile behaves in a pretty predictable way. As it moves further away, it should appear smaller, and as it moves closer to the frame, it should appear bigger. What makes drawing a tiled floor difficult is that the tile is down here, and in this orientation, one of the sides is further away from you, and therefore appears smaller, whereas another side is closer to you, and therefore appears bigger. And this deforms the shape of the tile into this kind of squat little trapezoid. So now the sides are not the same length, none of the angles are right angles, so all of our definitional properties of the square have been destroyed by viewing it in perspective. And that leaves us with really not very much guidance in terms of how to draw a square in perspective, let alone an entire tiled floor. But Alberti and others were able to figure out a general method for drawing a perfect tiled floor in perspective every time. And in order to do that, they had to make two important observations. The first is that while many of the properties of the square have been destroyed, one thing persists, and it's that all four sides are still straight lines. And this is a general property of straight lines in perspective. A straight line always looks straight. There's no way to look at it that makes it appear curved or bent. So if I twirl that, it might seem to change length, but it always looks like a straight line. And the other thing they observed had to do with parallel lines. And the idea of a parallel line is pretty intuitive. It's just a set of lines that go off in the same direction, like rails on a railroad track. And a property of parallel lines is that they don't meet. We know we could walk down this railroad track forever and we'd never have the rails come together. But if we look at it, they very clearly appear to meet. So this is an illusion regarding parallel lines. In perspective, parallel lines come together at a point. And it's not just rails on the ground. There's a lot of parallel lines in this scene, and all of them, whether they're on the ceiling or the walls or the ground, all seem to converge at the same point, which later became known as the vanishing point. So these are the two observations. Straight lines remain straight in perspective. All parallel lines meet at a vanishing point. And with these things in mind, we can now draw perfect checkered tiled floors. This was first published in 1436 by Alberti. He called it his legitimate construction. And what we're going to do is take this isometric view of a checkered tiled floor, and we're going to draw it on the right in perspective. So the first thing you need is to sketch in a horizon line with a vanishing point. The first step to this is pretty easy. The horizontal bottom of that floor is also horizontal in perspective. The tiles are evenly spaced across that line, and they're also evenly spaced across that line in perspective. But each of those dots is the base of a vertical line, and these are all parallel lines. So in our perspective view, these lines should all meet at the vanishing point. The next thing we do is set the height of our first row of tiles, and this can actually be anywhere you think it looks good. But the next part is the hard part. There's all these other horizontal lines, and they're evenly spaced in the isometric view, but in the perspective view, they should be getting gradually closer and closer together. So how do you get that right? So Alberti had a really clever trick for this. First, imagine this diagonal line. If you look in the lower left corner, it crosses diagonally the lower left tile. So we can actually start to draw this in our perspective view by making that diagonal. But because straight lines remain straight in perspective, we can get the rest of that line by just extending our starter. And that creates a number of other intersection points. And if we look at those intersection points on the left, they're crossed not just by vertical red lines, but also by horizontal green lines. So those are reference points for where to draw our horizontal lines. And that's all there is to it. Perfect, in perspective, checkered floor every time. So after this gets published, Renaissance painters start going crazy, putting tiled floors in all their paintings. Donatello actually put a tiled floor in a manger scene, which gives you some idea that this was just like the first special effect we'd ever discovered. If you organize a painting around a vanishing point, suddenly you have total command over depth and perspective. And this brings up an interesting question. What is a vanishing point? It's not out there in the world, and it's not even something you get to see. This red dot is the vanishing point of this scene. A vanishing point is just the center of a radial field of lines which covers your entire field of vision and organizes the scale and orientation of the objects. It's like a background geometry that governs how things should look in perspective. But once you can organize your painting around a vanishing point, you go from representing a dinner scene like this to the dinner scene looking like this. The vanishing point is just above Jesus' head, and if you look at the ceiling and the walls and the floor and the table, everything is perfectly lined up. So the more artists played with this, the more interesting things they discovered about the vanishing point. For instance, if you're looking at a tiled floor from an angle, some of these lines will head off to a vanishing point on the left, but the other set of lines head to a vanishing point on the right. So you can actually have two vanishing points in the same scene. This is called two-point perspective, and it's a standard way of representing a rectilinear object when viewed at an angle. Here's a drawing that makes use of three distinct vanishing points. And actually, it turns out that you need at least one vanishing point to have your scene in perspective, but after that you can add as many as you want, and they all play nicely together. Here's a staircase based on 6 distinct vanishing points. If you have a lot of crap in your scene, you can have like 24. And there's a situation I think we've all been in where we've actually seen a lot of vanishing points, and that's when you're driving down the road next to like a vineyard, and you see these stripes in the grid on in the field, and these almost seem to keep up with you. It's every possible route through the field has its own vanishing point. And this is kind of a cleaned up version of what that looks like. So it's as if the entire horizon is just dense with potential vanishing points. And the greatest thing is they're not even laid out evenly. They're in this kind of progressive, sort of recursive structure. And it's important to keep in mind that this is not there in the isometric view. Your eye is responsible for somehow bringing all this additional structure out of the grid. And things get even crazier if you go from having these lines in a field to having dots filling up a three-dimensional grid. If we fly into this and view it in perspective, we actually see this crazy psychedelic pattern. And there's not just vanishing points now, there's vanishing lines and vanishing triangles, and it all looks a little wacky. But if you play with it a little bit, you see it's kind of like graph paper for drawing things in perspective. So if the vanishing point and its radial lines are sort of the underlying geometry of single point perspective, this is a much more general grid of your visual distortion field when you're viewing things in perspective. And you can see that it looks very geometrically rich. So this would be an interesting thing to understand a little bit better. So in the 17th century, what happened was the theory of perspective moved from the world of fine arts to the world of mathematics. And 17th century mathematicians came up with some pretty clever ways of thinking about this geometry. So here's one important insight they had. Let's take a white tiled square, or tile square, and illuminate it so it casts a shadow. Now, if we move it back and forth, you'll notice the shadow gets bigger and smaller. And this is sort of reminiscent of what was happening when we were viewing it in perspective. And in fact, it turns out that any outline that a shape can give to your eye in perspective corresponds to a possible shadow that that object can cast. And this is a huge conceptual step forward because perspective is all in your eye, but shadows actually exist. You can trace them, you can measure them, you can think about them conceptually. You know, this is a square, which means 4 equal sides and 4 right angles. And while it may appear to take on different shapes, if you reach out and measure it, it's always right angles and those same lengths. But the shadow you can measure, and you can certify that it does not preserve the lengths of the object casting the shadow, doesn't preserve angles, it does not even preserve proportions. And the whole problem with coming up with the geometry of shadows is that they don't appear to obey any geometric rules at all, necessarily. In geometry, you talk about parallel lines and circles. Circles have constant radius, and you can hold up a circle to cast a circular shadow. You can hold up a parallel line to cast parallel shadows. But then if you spin those things around, parallelism goes away, the circle turns into an ellipse and flattens out. So if we want to come up with a geometry of shadows, we have to come up with something we can say about shadows that stays true even if the object casting the shadow gets rotated around. And it turns out there's a whole bunch of things you can say. There's a field called projective geometry which is dedicated to this. Unfortunately, the theorems of projective geometry are kind of a mouthful, so bear with me. Imagine an object is casting the following shadow. There's a dot, 3 lines going through it. It has a triangle which has 1 corner on each of those lines, and a second triangle which also has 1 corner on each of those 3 lines. Now, without knowing anything about what's casting this shadow, here's something we can say about these 2 triangles. If we take their longest sides, we can extend them and they'll cross in a point. If we take the upper sides, those will also cross in a point, and if we take the remaining sides, those will cross in a point as well. Generally, 3 points do not lie on a line, but these ones always do. And this is an intrinsic geometric property of these shadows. So it doesn't matter how we reorient the original object, those 3 intersections always line up. And this is actually a property of plane geometry. It's called the Desargues theorem. And even if I adjust the original lines, like change that one, the intersection just moves along on the dotted line. If I adjust the triangles, the line itself moves. This is a generic property of points, triangles, and lines in the plane. And when you're confronted with a kind of abstract geometric result like this, a very reasonable criticism is to say, who cares? Where would you ever see this? But the irony in this case is that you're actually seeing this all the time. If you look at any checkered floor, you can find examples of these Desarguian triangles in it. And if you extend the edges of these triangles, you get a line of intersections that we normally call the horizon. So the Desargues theorem gives us a geometric foundation for understanding why the horizon is so straight. And what's interesting is that we'd been doing geometry for 2,000 years at this point, and we had never observed this before, because it turns out you have to think about this in terms of shadows in order to prove it. So by trying to understand the geometry of our vision, we opened up a whole new world of geometrical theorems, which had actually been literally hidden in plain sight the whole time. There's also Desarguian triangles all over the place in here. In fact, this is one of the dominant motifs of this weird pattern. So this is just the beginning of projective geometry, which has been going strong for about 3 centuries now. This has been one of the richest veins of mathematical insight. There's hardly any field of mathematics this hasn't touched. And we opened up this chain of abstractions by first just asking, why do things get big when I hold them close to my face? This all started with Alberti's veil, which means this veil is one of the most important events in the history of mathematics. But it's also important for another reason. Arguably, Alberti's veil is the first camera. The cameras we have today are the result of incremental improvements to this idea. And in fact, this, like all subsequent cameras, is basically just a machine for taking a 3-dimensional space and converting it into a 2-dimensional image. What came after Alberti's veil was a room with a pinhole punched in it, and the artist would trace the shadow on the wall. This was what Kepler called the camera obscura, and we continued to call it a camera even when the artist had been replaced with film in the 19th century and we had our proper modern cameras. We call it a camera whether it's black and white or color, whether it's shooting film or stills, whether it's one of these digital networked lenses that we all carry around. Cameras are optical eyes. They see the world the way we do, and they're fooled by the same tricks that we're fooled by. So if you show something in forced perspective, this is our exhibit, big chair, little chair. So going from left to right, each of those chairs is twice as tall as the one before it. But if you line them up just right, you can make them look like they're the same size, or you can take a picture which also images them at the same size. But when you have a camera, you can actually do other tricks with perspective that just aren't possible with your eye alone. So imagine we're looking at this orange square tube through a camera, and now we're going to back way, way up. And what happens, obviously, is that the tube appears to get really small. But with a camera, you can attach a zoom lens and blow it back up to that original size. But if we compare the tube viewed from a distance with a zoom lens to what it looks like viewed close up, we see they're not quite the same. The one on the right looks like it has kind of a wider mouth. It's sort of blown up, whereas the one on the left actually appears a little bit more isometric. And this gets at a pretty interesting property of perspective, which is that most of your foreshortening distortions are happening very close to you. When you lie down in the grass, you can make the grass appear like it's almost the size of a tree, and that's a very big distortion. But if you're looking at something from a distance, some of these houses might be miles apart, but they all look like they're in proper scale if you yourself are standing sufficiently far away when you're looking at them. And that leads to an interesting idea. What would it look like if I dollied back from this square tube and zoomed in such a way that it was kept at constant scale? Then the only thing that appears to change is that the amount of perspective in the scene is getting dialed up and down. So in 1958, on the set of Alfred Hitchcock's Vertigo, James Stewart was playing an acrophobic private detective, and focus compensated zoom lenses had improved enough that they could kind of hang it over the stairwell, pull it back and zoom in and create this crazy distorting effect. And if you were a film goer in 1958, this was maybe the craziest thing you'd ever seen. This was $19,000. It's less than a second of film, and it was created by an uncredited second unit cameraman named Erman Roberts. But it became a classic cinematic shot. This is used in Jaws, one of its most famous uses. This is Roy Scheider, and he's watching some kids get eaten by sharks, and he suddenly had this moment where he realizes there's a shark in the water, and the whole world sort of blows up around him. This is called the dolly zoom, and it's a way of signaling that a character in a movie is undergoing some kind of epiphany or shock or nausea or orgasm. And it became a part of our sort of cinematic vocabulary. It was a simple signal, and it actually started to get way overused. This is kind of an absurd dolly zoom montage from The Quick and the Dead. I think by the 90s it had started to seem like kind of a gimmick or a cliche, and I don't even know if they use this anymore in movies. But we've noticed for a while that we have a really great runway for doing dolly zooms out on our south apron with Treasure Island in the background. So this is one of our explainers, Wit, and we made a dolly zoom of him. And the thing to notice is that Treasure Island starts out as like a little dot behind his head, and we can blow it up to like his entire backdrop. There's also kind of a cool accordion thing that happens with the railing there. So, for instance, this is what big chair, little chair look like far away and zoomed in. This is sort of an isometric view of those chairs. And this is what they look like kind of close up. And you can use a dolly zoom to kind of continuously ratchet between different perspective views of those chairs. And that's actually all the slides I have. So, thanks, everybody.